Dear friends, today we are going to discuss about Weber cycle. This is a very important power cycle used for the generation of power in mainly thermal power plant and in nuclear power plant. Because in nuclear power plant where vapor means water used as a working fluid. This power cycle is used. It is a Rankine cycle. That is known as a vapor power cycle. This cycle is very efficient compared to Brayton cycle or any other cycle because it is a practical cycle because it is we know that for given temperature limit Carnot cycle is most efficient, but it cannot be used for the vapor power cycle due to certain practical issues and impracticability. We can't use Carnot cycle for power generation. So vapor power cycle, it is also known as a Rankine cycle, is a most popular cycle used for the generation of power in thermal power plant or in nuclear power plant where water is used as a vacuum. How it works and how in thermal power plant what is a working principle of thermal power plant that we are going to discuss in today's discussion. So it is also very important topic from the Indian engineering services point of view or public sector examination, particularly in BARC. Use this question from this topic always asked by interview panel. So you must prepare for this because you will certainly find one question from GATE examination and one question from Indian engineering service examination, and you can't miss one question even Indian civil service examination if you opt for mechanical engineering as optional subject. So this topic is going to be very useful for you because concept will be clear. We are going to cover in this topic simple vapor power cycle, single step and reheat cycle, regenerative cycle and combination of reheat and regenerative cycle. All cycles we will discuss in incoming lectures. So let us start what is a vapor power cycle. First we draw a schematic for working of the thermal power plant, then we will define how this process can be represented on a TF diagram and enthalpy entropy diagram, that is Mollier by using Mollier chart and the PV diagram. All these diagrams we will discuss, and we will also discuss what are practical limit of temperature and pressure in this cycle. So let us first draw a schematic. So see, this is a schematic of the vapor power cycle based thermal power plant. You can see there are four main components. This is first it is a boiler plus a furnace where combustion will take place of the fuel in presence of air and combustion product will come out, and heat generated is supplied to the boiler for heating of the water. And you can say here steam will be generated and steam will supply to the turbine. So here turbine steam will enter into the turbine, the high pressure to low pressure, and it expand in the turbine. So pressure and pressure energy and thermal energy of the steam will expand, so pressure will drop, and this due to reaction of the expanding steam, pressure difference will take place inside this turbine rotor. So mechanical work generated here and it will rotate and it is connected with the generator. So generator will also rotate with the same shaft, and generator there is a high tensor line connected with the generator. So next steam at low pressure will enter into the condenser. Condenser is maintained at low pressure. So it will here steam will be condensed in presence of the cold water supplied from the river or cooling tower. If there is a large source available of the river or canal, you can take large quantity of water for cooling of the steam. So steam condensate here at high temperature. So if this condensate steam, which is a higher temperature compared to surrounding temperature or fresh water that is supplied from the river. So this high temperature condensate is pumped back at higher pressure to the boiler. So you can see this is working of the cycle, and this system works in closed cycle. You can represent in this all four process. Process 1 to 2 is steam expansion and turbine work will be there, WT, and process 2, 3 condensation condensation process. Here exhaust steam enter into the condenser, so it cool down, and the condensate will be collected by the pump, so energy will be supplied to run this. So here you are providing input of power and heat generated here supplied to the boiler. So this is a working of the, and this cycle you can represent, this cycle represent in the, like a engine, cyclic engine. So let us see how same cycle we can represent in closed cycle, like a internal, like a Carnot cycle. So this system is working in closed cycle. So you can see see this is the closed cycle. Here you can see this is a closed cycle, and turbine, condenser, pump, and boiler. So heat is supplied from the source, means furnace, to the boiler, that is amount Q1, and boiler will generate steam, and steam is supplied to turbine. Turbine expands, so work, this is process 1, work is done by turbine, so WT you will get, and in process 2 to 3, that is a condensation process. From turbine to condenser, steam, exhaust steam will enter into the condenser, and in this process heat will be released from the condenser to the sink, and this is a sink. This is not a condenser, but it is a sink. It is a sink, means river or some large reservoir where heat is supplied from condenser to the sink, and from condenser it comes to the pump. So to run the pump, work is supplied to run the pump, and pump will supply again this H2O, that is liquid state H2O, to the boiler. So this is the complete cycle. In this cycle you can see one thing you will know, that for cyclic process, net work done equal to net heat supply. For cyclic process, we know sigma W equal to sigma Q. This is always applied for the cyclic process. Sigma W equal to sigma Q. So W means WT minus WP equal to Q1 minus Q2. This equation is always equal. You can use any value, WT minus WP, that is a net work done in this process, equal to Q1 minus Q2. This is applied for any closed cyclic process. So how we can find out thermal efficiency? Thermal efficiency of this system and thermal equal to W net upon input of energy. How much input is given in this cyclic process? W net already we know, WT minus WP upon input is only input that's given, that is Q1. From furnace we supplied Q1 energy, that is heat generated during burning of fuel in presence of air, that Q1 is supplied to the boiler. Only input is that is a Q1. So that is a, this is, you can also write W net upon Q1. W net upon Q1. So this is a very simple equation. From this you can find out, we can also express all this process in Rankine cycle. How this Rankine? Because this process will define, because all four processes that are occurring in boiler to turbine to the condenser and pump, how we can represent all these four processes by cycle. So this cycle is known as a Rankine cycle. And Rankine cycle will also calculate thermal efficiency. So let us now define through Rankine cycle. Starting from here, 4 to 1, H4 plus Q1, steady flow energy equation for boiler. Process 4 to 1. Taking 1 kg of H2O, means unit mass working fluid is there. So H4, you say starting from here 4 to 1. What is happening? Apply steady flow energy equation for 4 to 1. H4 plus Q1 equal to H1. So Q1 equal to H1 minus H4. Q1 equal to H1 minus H4. Again applying steady flow energy equation for 1 to 2. Steady flow energy equation for process 1 to 2. Steady flow energy equation for process 1 to 2. Here 1 to 2. Steady flow energy equation process for 1 to 2. So here H1 equal to WT plus H2. So here you get Wt equal to H1 minus H2. H1 minus H2. Again applying steady flow energy equation for process 2 to 3. For 2 to 3, steady flow energy equation apply for 2 to 3. H2 equal to Q2 plus H3. So Q2 equal to H2 minus H3. Again applying steady flow energy equation for process 3 to 4. For process steady flow energy equation for process 3 to 4, you will get H3 plus Wp equal to H4. So Wp equal to H4 minus F3. All these equations you get. Here we have find Wt equal to H1 minus H2 and Wp equal to H4 minus F3 and Q1 equal to H1 minus H2. So now define thermal efficiency in terms of the enthalpy. So let us define thermal efficiency in terms of the enthalpy. Already we have defined thermal efficiency of system equal to W net upon Q1. So W net equal to Wt minus Wp upon Q1. That is equal to H1 minus H2 minus H4 minus H3 upon H1 minus H2. This is a thermal efficiency in terms of the enthalpy, because actually in actual problem solving you have to use this equation. For solving you have to use W net and Q1, and you have to find out W turbine work and pump work and Q1 from the enthalpy chart. That is, most of the time you will find table given of the enthalpy and steam property will be given. You have to find values from the steam table, because nowadays it has now become old practice to provide you molar chart, steam table, because competitive examination, if all students will find values, everyone will have different answers, so it will be difficult. That's why in competitive examination you will be provided table, and from table if you calculate values, you will find, all students will find, if the answer is correct, same value. That's why you have to practice how to find values from the table. So now define this. You can also define thermal efficiency in terms of the TS, temperature entropy diagram. So let us draw temperature entropy diagram of all these four processes. This is temperature in Kelvin and this is entropy. That is, you have to entropy is kilojoule per Kelvin kg. If there is a specific entropy, then kilojoule per Kelvin kg Kelvin you can say. Temperature T is absolute temperature. If you draw TF diagram, you will find like this TF diagram, and you can draw all four processes on TF diagram. Process 1 and 2, 3, 4, this is a pressure P1 and this is a pressure P2. So let us taking another color. You see from the process 4, 1 to T is expansion process, isentropic expansion process in turbine. So here you will get Wt, and 2 to 3 is a condenser process. Here heat will be released, that is a Q2, and 3 to 4 is a pumping process. Here work is done, Wp, and 4 to 1 is a constant pressure heat addition process. So Q1 is supplied. Q1, that is a Q1 will be also included here to this point. Q1 means whole of the area of this diagram. Area Q1 means क्या हो जाएगा? Q1 equal to area under curve is a 1, 2. Here you can take 4 and 5 and 6. 1, 2, 5, 6 and 4. Whole area will come under Q1. 1, 2, 5, 6, 4. That is a whole area, because heat reaction process taking place from 4 to 1. So whole of the area will come under this process. And Q2, heat rejection process. Q2 means condensation process start from 2 to 3. So this area, only this area will come. Q2 क्या हो जाएगा? Q2 equal to area under area of the 2, 5, 6 and 3. Only this area. 2, 5, 6 and this rectangular area will come under the heat rejection process. So net W net कितना होगा? W net equal to already we have Q1 minus Q2. Q1 minus Q2. Whole area minus this area. Whole area of this curve minus this area will come. That is known as a W net. This area, only this area is a W net. Only this area is a, you can further. Only this area is a W net. This area 1, 2, 3, 4, 1. 1, 2, 3, 4, 1. This area is known as a W net. Net work done. And this is a heat rejection. 2, 5, 6, 3 is a heat rejected. Overall heat is given 1, 2, 5, 6, 4. So on the basis of area, you can show what is the thermal efficiency. N thermal, you can again N thermal equal to W net upon Q1 equal to area 1, 2, 3, 4 upon area 1, 2, 5, 6, 3 and 4. So on the basis of area on TF diagram, you can represent thermal efficiency. I think this concept is also clear. So how this cycle can be shown on the TF diagram and HF diagram, and considering all possible expansion process through turbine under ideal and real conditions. So let us try to explain, because actually this cycle will be useful for you to interpret the various processes through TF diagram or HF diagram, that is also known as a Mollier chart. So representing thermal processes that is occurring in vapor power cycle in thermal power plant on TF diagram, HF diagram and PV diagram. PV diagram is only for the showing, but it is not useful, never used for the solving the problem. Here we are representing how we can represent this process on PV diagram. So first it is a PV diagram, TF diagram and HF diagram. You can see there are three diagrams on which I want to represent thermal vapor power cycle. So you can see this is a representation of the vapor power cycle on PV diagram, TF diagram and HF diagram. These two diagrams are most frequently used for the calculation purpose, and this one is only for the representation of the on PV diagram. This is not never used. I think you will not find any application of this only how we represent vapor power cycle on PV diagram. So let us see here TF diagram. You can see on TF diagram either process will start. This 4 to 1 is a heat addition process. 4 to 1. 4 to 1 is a constant pressure heat addition process. Either in turbine, just as saturated state expansion will take place and up to the moisture limit, and from the we can take some superheated state in turbine expansion, and again after expansion in turbine some moisture content will be there. So this moisture content is not should not be more than 85%, मतलब 15%, means not more than here quality of steam should not fall below 85%. So that is a condition on which steam turbine operates. So there are three conditions. Either you represent on TF diagram or HF diagram. You can see any one. Here you can see this is HF diagram. So process either start from the superheated state to some after expansion, some moisture content will be there. You see here this moisture content should not be more than 2, should be equal to 0.85. Quality should be fixed 0.85, means 85% steam and 15% moisture. So this is a, and if you start from here, quality is less than 0.85, it is advisable that you have to take some superheated steam and then expand it turbine, and you will reach up to the 85%. Here condensation process will start, and up to 3 complete condensation will take place, and from 3 to 4 is a pumping process, and water is pumped to the empty condition 4 into the boiler at high pressure, and from here heat addition process will take place. Heat addition process 4 to 1 is a constant pressure. that is a P1, this is a P2 and this is a P1. This is a P1 and this is a P2. This is a P1 and this is a P2. P1 higher than P2. P1 is a boiler pressure and P2 is a condenser pressure. So any one cycle you can take, but this cycle you must, every student, everyone must know how to draw TF diagram and HS diagram and how to interpret each point. This is a saturation state, this is a superheated state, this is a expansion after steam will enter at the condenser, and from here to here it is a condenser process. Steam will completely condense, and from heat 4 is again pumping will take place. Pump will raise the pressure because pressure is here higher, here is low pressure. So pump work is to transport water from the condenser to the boiler at higher pressure because these two pressure level are different. So this is how we can represent these processes on this diagram. I think this is sufficient because the video is going larger. So in next edition we will define how pressure and temperature are limited by mean pressure, and how we calculate steam rate, thermal efficiency and heat rate and work ratio in next lecture. Thank you very much for watching this video. If you like, please leave your comment and also share it to your friend. Thank you very much.